then the solution should just award everyone the same. Okay? So if they're in exactly the same positions, then they should be paid the same. Okay. Scale invariance is a little bit more tricky, but this says that says the following. Let's suppose we have a problem, say BD, and we choose to solve this in this fashion, right? Now, if we were to simply change the scale in which we measure, say, player one's payoff. So all of a sudden, we're going to change the unit in which we measure player one's payoff from dollars to 50-cent pieces. Then scale invariance means that, well, if before at this solution, player one was going to get $100, now when we simply rescale, we don't change the problem in any substantive way, we simply rescale the horizontal axis, and we're counting in 50-cent pieces, then it should be the case that player one receives, whatever I said before, $100, now they should receive 250-cent pieces. Okay? That if we rescale the problem, the solution should change in the same way. It shouldn't be fooled by changing the unit of account. Okay? Or if arbitrarily, instead of counting $100 in dollars versus 50-cent pieces, we were to just raise the dollar value by, say, $10 for person one and recalibrate that way, then the solution should just give player one an additional $10. It's not changing the substance of the problem. It's not really changing the outcome. It's just really changing the scale or level along which player one's payoff is measured. Okay? So this means that the solution should be invariant with respect to, or it shouldn't be fooled by scale changes or translations. Okay. Now this is is a bit more complicated. You can let me know, or you can think about whether or not this seems like a reasonable property for a solution. Okay? So this is saying the following. Let's suppose that we have a game, BD. Okay? Let's suppose that we solve that game, not a game, but a bargaining problem, BD, and we solve that bargaining problem in this fashion, right? Now suppose we shrink the bargaining set to B prime. So we consider a subset of B prime. The disagreement point doesn't change at all. But this solution to the larger problem, BD, is still contained in B prime. So we shrink B prime down, but the solution to the larger problem remains in the smaller problem. IIA, independence of a relevant alternative, says that then the solution to the smaller problem should be the same. It shouldn't change. Okay? I think this is the way I think of this, that if this is deemed the best in the larger problem, and we shrink the larger problem down, but that best is still feasible, then this should also be seen to be the best in the smaller problem. Again, if it's deemed the best in the larger problem, and it's still feasible in the smaller problem, then it should also be the best in the smaller problem. Okay? That means that everything else is irrelevant. This is the explanation for the phrase irrelevant alternatives. The other alternatives are irrelevant. If the best among the larger is still feasible for the smaller, then that should be how we choose to solve the smaller as well. Okay? Okay, and Nash established that not only does this maximizer of the product of payoff gains, that is the Nash solution, satisfy those properties, but it's the only solution that satisfies those properties. So if we think that these are reasonable properties for a solution to the cooperative bargaining game, we have no choice but to adopt the Nash solution. And again, this is a very, very strong theorem because it's easier to get people to agree to certain sort of reasonable or minimal conditions or requirements for a good solution than it is to get people to agree to a formula. People don't look at a formula and say, oh, that's obviously the way we should solve this problem. But people would agree, perhaps, that Pareto optimality, they would agree to a principle. Pareto optimality is one of the properties that we think should be satisfied by a good solution. And symmetry is a reasonable property. We can agree to that if the problem is entirely symmetric, then the solution should be as well. And this, that we shouldn't be fooled by the unit of measure. If we count in 50-cent pieces versus dollars, then it should effectively be the same problem. And again, if we have a solution to a large problem that remains feasible when we shrink the problem, then that should be deemed best among the smaller opportunity set as well. So it's easier to get people to agree to good properties or what they think are the properties of a good solution than it is to agree to some sort of algebraic formula. But that being the case, this forces them to adopt that formula, because if they agree to these principles, they have no choice but to use the Nash bargaining solution to resolve these cooperative bargaining problems. Okay? So there's a proof of this. I'll post that on the Blackboard site. It's a bit difficult, but you can glance at it. I won't hold you responsible for the details of the proof, but I will sort of offer it to you, and if you have questions, you can ask. And again, this is called an axiomatic characterization, that not only are we listing properties that a good solution should satisfy, and not only are we establishing that the Nash, in this case, the Nash solution satisfies those problems, but this phrase axiomatic characterization means that those axioms uniquely identify or uniquely pick out that solution. They characterize that solution. Okay. Now, let me give you an argument against IIA. Okay. And again, at sort of first glance, IIA might seem compelling, that if a point is deemed best among a larger set and it still remains feasible in a smaller set, then it should be deemed best in the smaller as well. But here's an argument against that, and you can decide which is a more compelling argument. Okay? So here's the problem, and B is this entire triangle, and so there's B and there's a subset of B, but the disagreement point will remain the origin, will remain 0. Okay, so B is the whole problem with the disagreement point 0, the origin, and the Nash solution by Pareto optimality and symmetry. By Pareto optimality, the Nash solution must lie on the northeast boundary, and by symmetry, since B is entirely symmetric, this must be the Nash solution. So if this does satisfy those properties, then the Nash solution picks out this one. And it's also easy to see that given the symmetry of the problem, that the highest rectangular hyperbola will occur along the 45-degree line. Okay? So here is our problem BD. Here is the Nash solution to that problem. And now let's suppose that we shrink the problem down to B prime. So we cut off this top half of the triangle. Okay? And so the problem B prime, D prime consists of this trapezoid together with this disagreement point. The disagreement point remains the same. B prime is a subset of B. And moreover, this point remains feasible in B prime. So by IIA, by independence of irrelevant alternatives, the solution to the smaller problem must coincide with the solution to the larger problem. And indeed, that is the case for the Nash solution, that this is, again, the highest rectangular hyperbola one could reach over B prime. Okay? Okay, but look at the truncation once again. So this was the original problem, with the disagreement point being the origin, and this is the truncated or the subset, the smaller problem. notice that all of the payoff vectors that we eliminated in shrinking B down to B prime were those that were best for player 2, were most advantageous for player 2. So this is the overall best possible outcome for player 2. This is the overall best possible outcome for player 1. This portion these are the payoff vectors that are more favorable to 2 and less favorable to 1. Okay? And what we've cut off are all of those best possibilities for player 2. Well, one might think that in some sense, the player 2 is in a worse bargaining position here than they were here. That player 1 is just as strong. All of its sort of outside or other opportunities are still intact, but player 2's other opportunities or best outcomes have shrunk. And so the problem seems to have sort of changed in 1's favor, or at least in 2's disfavor, in a way that was disfavorable or unfavorable for player 2. Okay? So perhaps instead of the solution being the same, since this problem is now more favorable, relatively more favorable for 1 than for 2, or conversely, less favorable for 2 than for 1, perhaps the solution should change in 1's favor, that 1 is in a better bargaining position here than they were here. Here, by construction, they were in exactly symmetric bargaining position.